In this chapter, we'll talk about deadlocks. For example, a thread requests resources. If the resources are not available at that time, the thread enters a waiting state. Sometimes, a waiting thread can never again change state because the resources it has requested are held by other waiting threads. So this situation is called deadlock. A system consists of a finite number of resources to be distributed among a number of competing threads. The resources may be partitioned into several types, each consisting of some number of identical instances. CPU cycles, files, and the I/O devices are examples of resource types. Each resource type has multiple instances. A thread may utilize a resource in only the following sequence. The thread requests the resource. If the request cannot be granted immediately, then the requesting thread must wait until it can acquire the resource. The thread can operate on the resource, so use this resource. And when finished, the thread releases the resource. Let's take a look of deadlock with semaphores. Let's first review what is semaphore. Semaphore is an integer variable and has two atomic operations, wait and signal. In the wait method, we have a while loop. While that integer is less or equal than 0, and we see there's a semicolon after the condition. So that means if the integer is less or equal than 0, there's no operation. It just stops there. If that integer is greater than 0, then the integer will decrease by 1, so s minus minus. In the signal operation, we just increment this integer. Please click on the video to see an example deadlock in semaphore. A deadlock occurs if the four conditions hold true. The first one is a mutual exclusion. There should be a resource that can only be held by one process at a time. Hold and wait. A process can hold multiple resources and still request more resources from other processes which are holding them. No preemption. A resource cannot be preempted from a process by force. A resource can be released only voluntarily by the thread holding it, after that thread has completed its task. Circular wait. A process is waiting for the resource held by the second process, which is waiting for the resource held by the third process, and so on, till the last process is waiting for a resource held by the first process. This forms a circular chain. Deadlocks can be described more precisely in terms of a directed graph called a system resource allocation graph. This graph consists of a set of vertices V and a set of edges E. The set of V is partitioned into two different types of nodes. T from T1 to Tn is the set consisting of all active threads in the system. And R from R1 to Rm is the set consisting of all resources types in the system. So a directed edge from Ti to Rj is called a request edge. A directed edge Rj to Ti is called an assignment edge. The resource allocation graph shown here illustrates the following situation. There are one instance of R1, two instances of R2, one instance of R3, and 3 instances of R4. T1 holds 1 instance of R2 and is waiting for an instance of R1. T2 holds 1 instance of R1, 1 instance of R2, and is waiting for an instance of R3. T3 holds 1 instance of R3. Given the definition of a resource allocation graph, it can be shown that if the graph contains no cycles, then no thread in the system is deadlocked. If the graph does contain a cycle, then a deadlock may exist. If each resource type has several instances, then a cycle doesn't necessarily imply a deadlock has occurred. In this case, a cycle in a graph is a necessary but not a sufficient condition for the existing of deadlock. In this graph, there are 2 cycles exist. T1 to R1 to T2 to R3 to T3 to R2 to T1. Another cycle is T2 to R3 to T3 to R2 to T2. Thread T1, T2, and T3 are deadlocked. Thread T2 is waiting for the resource R3, which is held by thread T3. T3 is waiting for either T1 or T2 to release resource R2. In addition, T1 is waiting for thread T2 to release R1. In this resource allocation graph, there is also a cycle, T1 to R1 to T3 to R2 to T1. However, there is no deadlock. Thread T4 may release its instance of resource type R2. That resource can then be allocated to T3, breaking the cycle. Similarly, T2 can also release 1 instance of R1, and this instance can be allocated to T1 to break the cycle. In summary, if a graph contains no cycles, so that means no deadlock. If a graph contains a cycle, if only 1 instance per resource type, then there is deadlock. If several instances per resource type, there is possible a deadlock, but it's not necessary a deadlock. We can deal with the deadlock problem in one of 3 ways. We can ignore the problem altogether and pretend that deadlocks never occur in the system. We can use a protocol to prevent or avoid deadlocks, ensuring that the system will never enter a deadlocked state. We can allow the system to enter a deadlocked state, detect it, and recover. For a deadlock to occur, each of the 4 necessary conditions must hold. By ensuring that at least one of these conditions cannot hold, we can prevent the occurrence of a deadlock. Mutual exclusion. The mutual exclusion condition must hold. That is, at least one resource must be non-shareable. Shareable resources don't require mutual exclusive access and thus cannot be involved in a deadlock. For example, resources shared such as read-only files never lead to deadlocks. But resources like printers and tape drives need exclusive access by a single process. Hold and wait. In this condition, processes must be stopped from holding single or multiple resources while simultaneously waiting for one or more others. To prevent no preemption, if a process which is holding some resources requests another resource that cannot be immediately allocated to it, in that situation, all resources will be released. Preempt resource requires the list of resources for a process that is waiting. The process will be restarted only if it can regain its old resource and the new one that is requesting. If the process is requesting some other resource, when it is available, then it was given to the requesting process. If it is held by another process that is waiting for another resource, we release it and give it to the requesting process. For circular wait, it imposes a total ordering of all resource types. Circular wait also requires that every process requests resources in increasing order of enumeration. We will talk more about circular wait in next slide. To prevent circular wait, we assign each resource, for example, multi-x logs, a unique number. In this example, we assign 1 to first mutex and 5 to second mutex. And the resource must be acquired in order. That means a thread can initially request an instance of a resource, say Ri. After that, the thread can request an instance of resource Rj if and only if the Frj is greater than Fri. For example, using the function defined, a thread wants to use both first mutex and the second mutex at the same time. Must first request first mutex because the first mutex is 1, and then the second mutex, which is 5. Alternatively, we can require that a thread requesting an instance of resource Rj must have released any resource Ri, such as Fri is greater than Frj. In this example, we have a do work 1. In do work 1 method, we first request the first mutex, which is 1. Then we request the second mutex, which is 5. This is valid because 5 is greater than 1. Then when the thread releases the mutex, it first releases second mutex, then first mutex. So we're releasing the second mutex because the second one is 5, then first mutex, which is 1. We cannot do in this method do work 2 method because it requests the second mutex first, then first mutex. Also, it releases first mutex, then second mutex. So we cannot do in this order. Otherwise, there will be a deadlock. For deadlock avoidance, the simplest and the most useful model requires that each thread declare the maximum number of resources of each type that it may need. Given this prior information, it is possible to construct an algorithm that ensures that the system will never enter a deadlocked state. A deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that a circular wait condition can never exist. The resource allocation state is defined by the number of available and allocate resources and the maximum demands of the threads. A state is safe if the system can allocate resources to each thread up to its maximum in some order and still avoid a deadlock. More formally, a system is in a safe state only if there exists a safe sequence. A sequence of threads from T1, T2, until Tn is a safe sequence for the current allocation state if, for each Ti, the resource request that Ti can still make can be satisfied by the currently available resources plus the resources held by all Tj with j less than I. So in this situation, if the resources that Ti needs are not immediately available, then Ti can wait until all Tj have finished. When they are finished, Ti can obtain all of its needed resources, complete its designated task, return its allocated resources, and terminate. When Ti terminates, Ti plus 1 can obtain its needed resources, and so on. If no such sequence exists, then the system state is said to be unsafe. A safe state is not a deadlocked state. Conversely, a deadlocked state is an unsafe state. Not all unsafe states are deadlocks, however. To avoid deadlocks, we can ensure that the system will never enter an unsafe state. Given the concept of a safe state, we can define avoidance algorithms that ensure that the system will never deadlock. The idea is simply to ensure that the system will always remain in a safe state. If we have a resource allocation system with only one instance of each resource type, we can use a variant of resource allocation graph. For a resource allocation system with multiple instances of each resource type, we can use Banker's algorithm to avoid deadlock. In resource allocation graph, we introduce a new type of edge called claim edge. It's a dashed line. So a claim edge Ti to Rj indicates that thread Ti may request resource Rj at some time in the future. This edge resembles a request edge in direction, but is represented in the graph by a dashed line. When thread Ti requests resource Rj, the claim edge Ti to Rj is converted to a request edge. Convert the dashed line to a solid line. Similarly, when the resource Rj is released by Ti, the assignment edge Rj to Ti is converted to a claim edge Ti to Rj. So the solid line is converted to dashed line. The arrow direction also change. Note that resources must be claimed a priori in the system. Consider the resource allocation graph. On the left, we see T2 and T1 both request R2. Although R2 is currently free, we cannot allocate it to T2 at the right graph. Because from the right graph you can see this action will create a cycle in the graph. So a cycle, as mentioned, indicates the system is in an unsafe state. If T1 requests R2 and the T2 requests R1, then a deadlock will occur. In resource allocation graph algorithm, suppose that thread Ti requests a resource Rj. The request can be granted only if converting the request edge to an assignment edge doesn't result in the information of a cycle in the resource allocation graph. We illustrate the example in the previous slide. The resource allocation graph algorithm is not applicable to a resource allocation system with multiple instances of each resource type. For a resource with multiple instances, we can use Banker's algorithm. The name was chosen because the algorithm could be used in a banking system to ensure that the bank never allocated its available cash in such a way that it could no longer satisfy the needs of all its customers. When a new thread enters the system, it must declare the maximum number of instances of each resource type that it may need. This number may not exceed the total number of resources in the system. When a user requests a set of resources, the system must determine whether the allocation of these resources will leave the system in a safe state. If it will, the resources are allocated. Otherwise, the thread must wait until some other thread releases enough resources. When a thread gets all its resources, it must return them in a finite amount of time. The following data structures are used to implement the Banker's algorithm. Let n be the number of threads in the system, and m be the number of resource types. We have available, it is a 1D array of size m, indicating the number of available resources of each type. So available index j equal k means there are k instances of resource type rj. Max, it is a 2D array of size n multiply m that defines the maximum demand of each thread in a system. Max index I index j equal k means thread ti may request at most k instances of resource type rj. Allocation, it is a two-dimensional array of size n multiply m that defines the number of resources of each type currently allocated to each thread. Allocation index I index j equal k means thread ti is currently allocated k instances of resource type rj. Need is a 2D array of size n multiply m that indicates the remaining resource need of each thread. Need index I index j equal k means thread ti currently need k instances of resource type rj. Need index I index j equal max index I index j minus allocation index I and index j. Allocation I specify the resources currently allocated to thread ti, and the need I specify the additional resources that thread ti may still request to complete its task. Banker's algorithm consists of safety algorithm and the resource request algorithm. It is a safety algorithm used to check whether or not a system is in a safe state or follow the safe sequence in a Banker's algorithm. There are two vectors, work and finish, of length m and n in a safety algorithm. So the work is initialized to available vector. It has the length m indicates the number of available resources of each type. Finish I equal false for I equals 0, 1, 2, 3, until n minus 1. So all of the threads are not finished yet. Step 2. Find an index I such that both the conditions A and B satisfy. A is a finish, index I equals false, and B is a need I less or equal than work. If no such I exists, go to step 4. So step 2 check the availability status for each type of resource I. Step 3 is work equal work plus allocation I. Step 3 is to get a new resource allocation and add it to work. Finish I equal true and go back to step 2. In step 4, if finish I equals true for all the I, then the system is in a safe state. Please click on the link to view the safety algorithm example to have a better understanding of the algorithm. A resource request algorithm checks how a system will behave when a process makes each type of resource request in a system as a request matrix. Let's create a resource request array Ri for each thread Ti. If request ij equal k, then process Ti wants k instances of resource type Rj. If request I less than need I, go to step number 2. Otherwise, raise an error condition since the thread has exceeded its maximum claim. Step number 2. If request I less or equal than available, go to step 3. Otherwise, Ti must wait since the resources are not available. Number 3. Have the system pretend to have allocated the request resource to thread Ti by modifying the state as follows. So, minus the request from the available array, and also add the request to allocation array, and minus the request from the need array. If the resulting resource allocation state is safe, the transaction is completed, and thread Ti is allocated its resource. However, if the new state is unsafe, then Ti must wait for request. The old resource allocation state is restored. Please click on the link to see example. If a system doesn't employ either a deadlock prevention or a deadlock avoidance algorithm, then a deadlock situation may occur. In this environment, the system may provide an algorithm that examines the state of the system to determine whether a deadlock has occurred, an algorithm to recover from the deadlock. If all the resources have only a single instance, then a deadlock detection algorithm can be defined that mainly uses the variant of the resource allocation graph and is known as a wait-for graph. This wait-for graph is obtained from the resource allocation graph by removing its resource node and collapsing its appropriate edges. An edge from Ti to Tj in a wait-for graph simply implies that the process Ti is basically waiting for a process Tj in order to release a resource that it needs. An edge Ti Tj exists in a wait-for graph if and only if the corresponding resource allocation graph contains two edges, TiRQ and RQ, Tj for a resource, RQ. A deadlock exists in the system if and only if there's a cycle in the wait-for graph. The algorithm that is used to detect the cycle in a graph mainly requires n-squared operations, where n indicates the number of vertices in a graph. The previous scheme, that is, a waitful graph, is not applicable to resource allocation system having multiple instances of each resource type. Now we will move towards a deadlock detection algorithm that is applicable for such system. The algorithm mainly uses several time-varying data structures that are similar to those used in the banker's algorithm. And these are: first is available. It is an array of length m. It represents the number of available resources of each type. Allocation. It is an n multiply m matrix which represents the number of resources of each type currently allocated to each process. Request. It is an n multiply m matrix that is used to indicate the request of each process. If request index I index j equals to k, then thread ti is requesting k more instances of resource type rj. This is the detection algorithm. You can view the video below this video for the explanation of the algorithm. If the deadlocks occur frequently, then the detection algorithm shall be invoked frequently. Resources allocated to the deadlocked thread will be idle until the deadlock can be broken. In addition, the number of threads involved in the deadlock cycle may grow. If detection algorithm is invoked arbitrarily, there may be many cycles in resource graph, so we wouldn't be able to tell which of the many deadlocked threads cause the deadlock. When the deadlock detection algorithm determines that the deadlock has occurred in the system must recover from that deadlock. There are two approaches of breaking a deadlock. The first one is process termination. Process termination is to eliminate the deadlock. We can simply kill one or more process. For this, we use two methods. The first one is abort or the deadlocked process. Aborting all the process will certainly break the deadlock, but with a great expense. The deadlocked process may have computed for a long time, and the result of those partial computations must be discarded, and there is a probability to recalculate them later. Second one is abort one process at a time until deadlock is eliminated. Abort one deadlocked process at a time until deadlock cycle is eliminated from the system. Due to this method, there may be considerable overhead because after aborting each process, we have to run deadlock detection algorithm to check whether any process are still deadlocked. In resource preemption, to eliminate deadlocks using resource preemption, we preempt some resources from process and give those resources to other process. This method will raise these issues. First, selecting a victim. We must determine which resources and which process are to be preempted, and also the order to minimize the cost. Second issue is rollback. We must determine what should be done with the process from which resources are preempted. One simple idea is total rollback. That means abort the process and restart it. Third issue is starvation. In a system, it may happen that some process is always picked as a victim. As a result, the process will never complete its designated task. This situation is called starvation and must be avoided. One solution is that a process must be picked as a victim only a finite number of times.